All right, so we started seeing quite a lot of new concepts the last time around. Let me just start by recalling what we covered. So we saw the notion of NP proofs, where there's a prover and a verifier. The prover is unbounded, computationally unbounded, and the verifier is polynomial time, no probabilistic, or just deterministic polynomial time. And they both have access to X, a statement X, and a language L. And the prover, tries to send a proof point that convinces the verifier that a statement X is in the language. So, for instance, the statement could be a square mod n, and the proof could be the square root of which verifier. Right. So this is NP proofs, and really, these guys had two properties: completeness, which says that true theorems always have proofs. Squares always have square roots, right? And soundness, which says that false theorems never have proofs. Non-squares don't have square roots. Right. Then we showed how to generalize this to interactive proofs. Well, IP, which is interactive proofs, which is basically saying, look, let the prover and the verifier interact as back and forth, which we know is in the real world more expressive than rather than me talking to you. You ask me questions and I get to answer and keep going. Let's just do more things. Right. So that's interactive proofs. And the prover is still unbounded. The verifier is, well, there are two changes, right? One, there is interaction between the prover and the verifier, number one. And number two, the verifier is probabilistic polynomial time. So he tosses coins. Right? So if he doesn't toss coins, of course you can collapse all the rounds into one. So really, randomness is what gives you the power. And you still have completeness and soundness. Completeness the same. Soundness is now probabilistic and says that for every X not in the language, for every false theorem, the probability that any prover P star manages to convince a verifier is at most some number, half, let's say, or exponentially small. Yes, that's called the soundness error. So just write it down. For every prover P star and for every X not in the language, the probability that the output of the verifier, yes, on interaction with P star, this is the interaction with P star, on input X is 1, which means accept, is at most some number S. So think of S as half. You can repeat it to get S as small as 2 to the minus. Okay. Right, so these are the two options. And then we said, well, okay, so this is interactive proofs. And any NP proof, any language with an NP proof also has an interactive proof by definition. What is interactive proof? Just send the proof along. Okay, that's that. But IP can capture many more things. So one of you, I'm not sure who, asked, can't you put everything in NP? Right? What is an example of something that you cannot prove in NP? And we said, well, the language of sort of chessboards. Where the white always has a winning strategy, just for example, is not believed to be in NP. It's in P space, and the really sort of amazing thing about IP is that it can capture much more than NP. In fact, it can capture this language, this sort of chess language, and that pretty much exactly characterizes. So this is, this is all I'm going to say about it, but it's a profound theorem. So none of this is obvious. None of what I'm saying, both directions are not obvious. Okay. So IP can do a lot. 3, really the reason why why we introduced interaction, right? The fundamental reason why we introduced interaction was to say that there is a way of proving things without revealing the proof itself. That's IP by itself doesn't capture this notion of hiding the witness. It's still a proof system, And a side effect of introducing IP turned out to be that this is a much sort of more expressive way of proving this, but that's kind of a side effect. The main purpose of introducing introduction was to study zero knowledge inductive proofs, which is exactly IP proofs, except you also require the property of zero knowledge. Right? So this is A, B. This is also A and B, but B is probabilistic. And you also need C, which is zero knowledge. Yes, so we've defined two variants of zero knowledge. One is sort of zero knowledge against honest verifiers, and we call honest verifiers zero knowledge. And C prime, the variant of this, is general zero knowledge. General or malicious verifier. Zero knowledge. Yes. So we came up with these two definitions. We'll recall the definitions in just a minute. This is a recap of what we did. Yeah. About definitions. We also showed protocols. Yes. Showed protocols. The one that I'm going to really sort of talk about today is the quadratic reciprocity protocol. IP is our knowledge IP for quadratic reciprocity, which is this language for pairs n and y, where y is square mod n, or rather there exists an x such that x, y equals y. In other words, yes. This is what we saw the protocol. We proved a couple of things about it. We proved that it's sound and complete, but we did not prove that it's zero knowledge. That's the starting point for sure. Okay, so let's recall the protocol. Let's recall the definition of zero knowledge. So what is a protocol? Maybe you can, some of you can refresh my memory. This is a statement, yeah. There's always a proof and verifier. You gotta write that down. And well, let me say this was a 3-message protocol. Nearly as minimally interactive as it can be. 2 is really minimally interactive. It's 3. The question is how did this go? Does anyone remember? I'll help, but better if you help me. That'd be idea. Anyone start over? Yes.
The purger will choose a random value and commit to it by sending the square of that random value to the verifier.
Good. So the prover chooses a random value r in z and stuff and sends r squared. Let's give it a name. Let's say z equals r squared 1. That's what it proves. This doesn't depend on y at all. It's just a random value. The verifier says, a bit b, which he picks at random again. Randomly. And the prover says, the prover is supposed to release the square root of z times y to the b. In other words, if b is 0, square root of z, which is just r. If b is 1, the square root of z times y, which is r times the square root of y. So the prover actually has to know the square root. Yes. So, what is the point of the prover if he knows nothing more than the verifier? So the prover needs to have some more power than the verifier, otherwise the verifier could have done everything himself. No need to try. So originally we said, look, the prover has unbounded power, computational power. Here we are saying the prover has more information than the verifier. If he has unbounded computational power, he can get this information himself, but all he needs is this square root of 1. Okay, that's what he needs. So Of course, this is square root of z, r times the square root of y. That's what he sends for p equals 1. And the verifier checks whether, call this w, if w equals w square equals zy to the b mod n, accept, otherwise reject. Yeah, that's a problem. Excellent. Yes. Great. Any questions about this? Yes.
What's the point of B?
What's the point of B?
Yes.
Good. The point of B is really zero knowledge. Right? So the way the verifier can interact with the prover, right, is you can run the prover. You can say, look, give me a message, right? I'm going to give you a B, and you give me a response. The point is that the verifier has one shot at picking a B. You can either pick a 0 or pick a 1 in any given interaction. If he picks a 0, he gets what? He gets R. Okay. He gets nothing. Right? He gets nothing about the statement. He doesn't know anything absolutely about the square root of y. If he picks 1, he gets R times the square root of y, which again is a random number. So he still gets no information about the square root of y. Right? So in either case, what he gets does not reveal anything about the square root of y, which is exactly what we want for zero knowledge. Think about it.
If you just picked 1,
Uh-huh.
also just always picked 1,
Ah.
and also don't have no information,
Ah.
or is that not true?
Good, very good. So then it's zero knowledge. Yes, our interaction just should convince you that that protocol should be zero knowledge. Is it sound? Let's think about it. Okay, let's think about it. What if he always picks 0? Is that sound? Sound meaning, if y is not a square, the verifier should not accept. Yes. It is pointless because if he always picks 0, he'll get a square root of r, independent of y. But your question is more interesting, which is what if he always picks 1? Yes. I claim that there is a cheating prover strategy which will convince the verifier who always picks 1. That's what I think. You think of one? Yes.
If you sneaky with Z and choose
Uh-huh.
something,
How?
you choose a Z such that when you multiply it by Y, you always get a square, but Z is not necessarily a square. So like R squared Y inverse.
Okay. So here's the cheating prover. He picks Z equals R squared divided by Y. R squared, say, divided by Y times Y inverse. Not it. The verifier has no clue that this is going on. It looks exactly the same as it would have otherwise. Well, actually, if Y is a non-square, it doesn't look exactly the same, right? In the actual case, it's supposed to be a square. Here, it's a non-square. But the verifier cannot tell. It's a polynomial time algorithm. In any case, the honest verifier doesn't check for anything at this point. And now he happily says 1. What does the cheating prover do? He says, look, I'm supposed to give you a square root of Z times Y. What is Z times Y? It's R squared. By the way, I know the square root. I give you R. And the verifier says, accept. Well, actually, he should not be very happy, but he accepts. Yes? Yeah. That's why. So the
He gets R squared, right?
say again?
He gets R squared.
He gets say again?
Z, which is R squared, no?
Z is now, in this interaction with this cheating prover, is R squared divided by Y. Right? So he can get R squared, but that's okay, because everyone knows Y, everyone can go from Z to Z times Y and the other way around, no problem. Right? That's okay. The point is, he is going to accept. He is going to be fooled by this cheating prover. That's no good. So this is subtle, right? This is a game between a cheating we're not in the communication game where there's an eavesdropper in the middle. Both parties are malicious not at the same time, right? But we need to secure the honest verifier against the cheating prover, soundness, and the honest prover against the cheating verifier, which is zero knowledge. We have to do both. So the one case will not guarantee soundness. On the other hand, you could say, look, let the verifier ask both queries, okay, 0 and 1, and the prover responds with both answers, okay. That would be sound, for sure, but it won't be zero knowledge because the verifier can divide the two responses and learn the square root. So this is the trade-off between, We will come to this in just a minute, okay? This is very important. This cheating prover strategy is extremely important. We'll come back to this. Okay, so what did we just talk? Completeness is complete. Okay, you can, I mean, if everyone acts honestly and Y is a quadratic residue, the verifier will accept. Soundness is what we just argued, in a sense, which is that pick any cheating prover P star. Right. Doesn't matter. Any cheating, potentially cheating P star. I don't care how computationally unbounded he is. Don't care. He sends a first message. Yes, Z. How did he come up with it? I don't know. Yes. The verifier. So this is something that one of our TAs pointed out yesterday. That you have to check. Reject. Yes. So you have to check. You have to do some sanity checks. And Z has to be relatively prime to N. Otherwise, you can start cheating. Okay. So pick any cheating probe. We start. It sends some number Z. It is in Zn star. Okay. So how did he pick it? I don't know. I have no idea. Suppose for a moment that this P star can produce an accepting answer to both the 0 challenge and the 1 challenge, right? So there are only 2 challenges. So let's say he can either answer incorrectly on both, or 1, or correctly on both. Suppose he manages to answer correctly on both, and that's when he always manages to convince the verifier, right? So P star sends some Z, guaranteed to be in Zn star. He produces the right answer on 0, which is basically a square root of Z. Yes, it has to be. And he also manages to produce the right answer on 1, which is square root of Z times Y. So if he can produce answer square root of Z and square root of Z times Y, that means that Y is in fact a square. The ratio between the two is the square root of Y, even more. So, if Y is not a square, contrapositive, no prover can answer both the 0 and the 1 challenge. In other words, for any fixed Z, right, he can either answer the 0 challenge or the 1 challenge, but not both. Right? This is a subtle difference between that and the. So there we argued that if the prover knew what the challenge was in advance, he could always prepare the first message so that he can answer correctly. But that's not the game the prover and the verifier are playing. The prover and the verifier are playing the game where the prover says, commit, here is the first message, now let me try to answer both challenges. So the claim here is that for every fixed first message, the prover can only answer one. In other words, the probability that any of these provers manages to convince the verifier is most high. So for every prover, it's done. The probability that this prover manages to convince the verifier is at most high. Yeah, something to think about. The order of the interactions matters greatly here. Right? If you sort of switch the two, if you switch the challenge and the first message, first and the second message, there is no summness anymore. That's what we saw. In some sense, that's why it's a 3-message protocol, not a 2-message protocol. Yes. Yeah, does this make sense? So in any such protocol, there is a commit phase. There is the first message that the prover says something. Then there's a space of challenges. And you prove that no single response, the response to no single challenge reveals any information. That's what we have to prove now. I haven't shown it quite yet. But the response to any 2 challenges is impossible unless the statement is in the language. That's something. That's what. Any other questions? Let's keep that in mind for in a minute. Any other questions that I can answer? Good? You're all comfortable? Okay. Now I want to show zero knowledge. Really, I'll jump to the deep end and I'll actually show zero knowledge against arbitrary verifiers, malicious verifiers. Okay, and what is a zero knowledge definition? Let's recall C prime, pre-C prime, zero knowledge definition. Right, so intuitively what we wanted to say is that if you look at the view of the verifier, which is what? Remember, how did we define the view of the verifier? We wanted to say that reveals nothing, sort of what we want to say. What is the view of the verifier? And clearly he sees the messages back and forth, that's a view. He also sees the coins that he tossed, potentially. So you have to include. And let's do a sidebar for a minute. Just so we are on the same page. What if the view of the verifier is defined to be just the messages that the verifier sees in the course of the interaction? Forget the coins. Who cares about the coins anyway? Right? Just the messages. And the definition here would say that there exists, for every cheating verifier in the start, there exists a simulator S, PPT simulator, PPT verifier, such that for every X, the following 2 distributions are indistinguishable. The simulator gets nothing but the statement, n comma y. It does not get the square root of y, just gets the statement. And yet, it can produce something that looks exactly like what the verifier sees in the interaction. So in other words, this produces something that looks exactly like the view of V star in an interaction between P and V star and equal X. Right? So this is the view of V star. The view is defined to be the coins and the messages that V star sees. Another way to say it, a more explicit way to say it, is that for every V star, there is a simulator PPT V star, there is a PPT simulator, such that for every X, in the language, yes, otherwise, there is no proof here. X not in the language. For every X in the language, and for every distinguisher D, for every PPT distinguisher D, the probability, the D given S of X outputs 1, minus the probability, the D given the view V star of X outputs 1 is negligible. It's negligible in the security problem. Okay, this is a blown up version of this. This is a shorthand for this. So. Yeah, this is what we want. Let's say for a moment that now we try to tinker with this definition, which we should for all. Whenever you see a definition, you should poke holes at it. Let's try for a couple of minutes. Okay. What if the view of V star is defined to be the messages that it sees? Okay, so how about the view star is a set of is a transcript. In the protocol, in a set of messages. Okay, fine. I claim that that's not the right definition. In the sense, you can come up with protocols that satisfy the zero knowledge definition, but they're clearly not zero knowledge. They clearly reveal information to the verifier. Okay, that's why this is not a good definition. Can we think of why that is the case? So your goal is to come up with a protocol, right? If you define view as just a transcript, you can show a simulator that produces the view, blah, 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 right? You can satisfy this definition. But if you stare at the protocol, it is not zero knowledge. It reveals everything to the verifier, basically. Another way to look at it, another way to say it is that for this protocol, if you define the view correctly, namely including the points of the verifier, the randomness of the verifier, and the transcript, you cannot produce a simulator. It's not zero knowledge, but it looks, with few. Yeah. Yes.
This won't work for this situation.
Uh-huh.
Let's say you just set up a prover and a verifier,
Uh-huh.
where the verifier just comes up with a random element of Zn star, squares it, sends it to the prover,
Mm-hmm.
and the prover sends back the square root.
Square root of the random element.
Yeah.
Uh-huh.
So it sends a random square, and then receives back
Square
the
root of
square
that.
root.
Yeah. Yeah.
And then producing that view,
You can.
Yeah.
Right. You
you should
can.
be able to do that.
Well, let me think about it for a second. In the case of an honest verifier, you can produce this. Just pick a number and square it, right? But for a malicious verifier, you cannot produce this view. Yes. Wait, let me think for a second. No, you still cannot produce this view, right? I mean, the malicious verifier says, it's a machine, it's a Turing machine. You run it, it produces some square, and I'm supposed to produce the square root of this guy. That's what the view looks like. There's no way the simulation can do it. So I wouldn't even be able to show that zero knowledge with this copy definition. Here's the protocol. Okay, tell me if it's zero knowledge or not. Okay, this is a general protocol. Okay, for any NP language, 3-coloring, SAT, whatever. Okay? So the prover is the verifier. Yeah, both of them have a statement, and the prover has a witness for the statement. So this is in our case it's n and y, and this is square root y. Okay? The verifier picks a public key of some encryption scheme together with a secret key. Yeah. And he says, here is the public key. Take it. And the prover would say, let me encrypt the witness W, which is the square root, under this public key, and send it over to the verifier. Okay. If you look at the transcript of this computation, it is, you can simulate. I mean, it reveals no information about anything in the world. Okay? Because why? Because this encryption scheme is semantically secure, so this encryption of the witness looks like an encryption of junk. So you would prove zero knowledge under the term, but is it zero knowledge? It isn't, because when the verifier gets this message, he knows the secret key. So he's going to decrypt and he's going to get the witness. It's clearly not zero knowledge, yes? But if you define it wrong, you will be able to prove all sorts of things. Another way to think about it is that this definition of a view corresponds to someone sitting in the middle. He only sees the messages going back and forth, right? And of course, this protocol is zero knowledge for such a eavesdropper, but that's not fundamentally not what we are looking at. Our adversaries are either of the two parties. Okay? And once you corrupt this guy, you can see the secret key, and then this is clearly not. You have to be careful what you define. Good. Okay. So, does everyone see what view has to include the points? Otherwise, you can do all sorts of trivial things. Okay. So with that, let us actually proceed to show that this guy is in fact comes to God or not. How would you show such a thing? Okay. So again, zero knowledge, to show zero knowledge, right? What do you have to show? You for every verifier V star, polynomial time verifier V star, you have to show a polynomial time simulator which does certain things, right? For every means that you have no control over this verifier, yes? You're given a verifier. It's a Turing machine, interactive Turing machine, yeah? It sends messages, You don't know what it is, you're just given it. You have to design a simulator. So that is up to you. Yes, I mean there exists a simulator means you have to, you have to be constructive, I have to show a simulator. So that's a question. So there is a verifier V star who sits on the right side and does something, and I have to show a question. No? Okay, good. I have to show a simulator. So the prover is honest. The verifier is the one that is malicious in this interaction. Right? So soundness, the prover is a malicious one. And zero knowledge, the verifier is the malicious one. Yeah. So okay. So you're given the verifier. Yes, there's no prover. That's fine. I have to design a simulator. What does the simulator do? It cannot sort of ignore the verifier and produce something. Yes, I mean that's not going to work. It has to somehow use the verifier's code, interact with the verifier potentially, and at the end output a tuple of elements which looks exactly like that three tuple together with the verifier's coins, random coins, which is basically R and B in this case, right? So R is it should just be in this case. Yes? The only random coin that the verifier fixes is the one bit. Yeah, that's my goal. The goal is clear. So the verifier is a Turing machine. It's a code, it's a C program, let's say. C program that sends and receives messages. Now I have to design something. So how would I possibly do that? Here's an idea. You send him a random square. So the simulator, what does he know? He knows n and y. He does not know the square root of y. Yeah, I mean, if you know the square root of y, you can always produce whatever you want. So simulator knows n and y. What can he do? He plays that protocol. He plays the prover in that protocol. He sends a square. And what does he get back from the verifier? He gets back some bit b. What is this bit b? Who knows? I mean, it could be really a random coin toss. Or it could be some complicated hash of the first message together with, the stock market from today and the weather report from tomorrow, blah, 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 blah. I don't really know what it is. I just produce it. So what does the simulator now do? What can she do? Well, if b is 0, it's very clear what it is, right? The simulator can send R, the simulator can say, well, look, this is a good transcript. R squared, B, and R, that looks like a reasonable. That looks exactly like what happened in the real interaction. Why? Because R squared is exactly what happened in the real interaction, right? That's the protocol. So, B is what the verifier produced. I mean, it could be random, not random, but it's what the verifier produced in the real interaction. The real proof. And given these two guys, there is a unique third message, sort of unique. It could be any square root of R squared, but modulo that, this is unique third message. And this looks good, this looks great. If B is 0, B happens to be 0, then this is, I'm good, done. What if B happens to be 1? Then what do I do? Well, I'm supposed to send the square root of, I'm supposed to send R times the square root of Y, which I have no idea what it is. But I should have no idea, right? So I only know Y, I don't know the square root of Y. And I'm polynomial time, so that doesn't seem to work. So what would you do?
send a random number, and that should be able to compute whether that is truly random or.
In the where? I mean, here?
Yeah, the simulator sends, even if there's one, sends in a random.
A random number.
Yeah.
Good. But the point is that then it won't look like what happened in a real interaction. In a real interaction, right, the square of this number, if b is 1, the square of this number is supposed to be this times y. That there is no real way. Yeah.
What is the random type of V star? Is it the same as the original run or is it?
Good question. So V star, okay, so very good. Okay. So what is V star? V star is a Turing machine. Turing machine has an input tape, it has a random tape, and it has a thing where he works. Yes. The Turing machine just comes to me. It's a design of a Turing machine. Yes. So the simulator takes this Turing machine and plays with it. In particular, he can put stuff in the random tape. Yes, that's perfectly fine. But whatever the simulator puts in that random tape had better look random. If it's not completely random, it has to at least be pseudo-random. Otherwise, the view won't look. Yeah, I mean that's why the random tape has to look at least random. Another way to think about it is that verifiers, they may not have a random tape at all. They might have a hard-coded random string encoded inside the C program. So they say, look, you know what? I don't need any randomness. Thank you very much. I already have it hard-coded in my C program. Yeah, so these are called non-uniform verifiers. So then these guys don't have any random tape. It just happens to be hard-coded in the system. So, yeah, either one.
Then S knows what B is going to be.
S knows what B is going to be. Ah. How does S know what B is going to be? If he can put stuff in the random tape, sure, fair enough, yes. But what if the verifier has B in its code and it's obfuscated? Okay? In the sense that when the simulator looks at this code, he has no idea where the B is actually stored. He has some B in its head. Maybe he actually doesn't have a B in its head. Maybe he computes the B as some complicated hash function applied on the person. He say, I don't know what B is. I'm just going to, wing it, when it comes time. Then what do you do? Then you're in a conundrum, right? If you knew what B was, you have a leverage, yes? But you don't know what B is until you have a leverage that you can pick the first message in a nice way, that you can answer that. But you don't know what B is unless you fix the first message. So it's a bit chicken. So look, there is an inherent contradiction here. Yes, awesome.
We can classify if it's x and r squared, if it's tails and r squared divided by y. And then if that doesn't work out, just try again with another random r.
Okay. Right. But let me get there in like 2 minutes. Okay. What is 2 minutes? The simulator, if you think about it, okay, he is in the role of the prover, right? He is the one that is supposed to play the prover in a sense. He doesn't know what y. He doesn't even know if y is a square or a non-square. Okay, and he has to produce a good transcript without knowing what y is. Yes, in a certain sense. So you're asking the simulator to produce an accepting transcript, yeah, even if y is a non-square. Which sounds like it shouldn't be possible. Yes. If the simulator can produce an accepting transcript when y is a non-square, why isn't the simulator the cheating prover? The protocol should be something. See what I'm saying? So the simulator needs to have more power than a prover. Otherwise, you can make him the cheating prover and soundness goes down the drain. what power does the simulator have? Like what could it possibly have? The point is, the prover can only interact with the verifier one-on-one. He says, look, here's a message, yes? Give me something, and then I give you something else. He cannot say, look, verifier, you know what, I have your code, I can mess with your brain. When you send me the second message, I'm going to rewind you somehow. I'm going to erase your state, rewind you to the first minute and say, look, you tell me something else. Okay, that the prover cannot do. Okay? The simulator, on the other hand, has the code. He can play. He can play with the code of the verifier. He can do whatever he wants. He can look inside the code, take it apart. That we're not going to do to the full verifier at this point. But he can run it many times. That's what, at the very least, yes, and run it many times. And that's what the simulator does. So let's do what. Let's try what Arsen did. Formally. Okay. So the simulator does the following. He picks a bit B prime, randomly from 0, 1. Yeah. B prime, you should think about it as a guess, as the simulator's guess as to what B is going to be. Okay. The best it can do is really randomly guess. And then he says, look, I am going to not always send R squared, I am going to send R squared times Y, whichever way it is, to the minus B prime. Doesn't really matter if it's plus or minus, I can do both ways. Right? So yeah, that's how I'll send the first message. Yes? So if you look at that first message, it looks exactly the same as the first message in that real protocol. That guy was a random square. This guy, of course, is a random square if Y is in the language. And in fact, we only require zero knowledge when the statement is in language. In other words, when Y is a square. So when Y is a square, this guy is true. Now the verifier says, you know what, let me take this first message, let me take the stock market, the weather report for tomorrow, hash the whole thing down, come up with a bit B. Okay? How does he do it? I have no clue. But he sends me a bit B. Okay. Now I say, if B equals B prime, then I'm golden. Okay? Why is that the case? What am I supposed to send here? I'm supposed to send the square root of Z times Y. Yes. Y to the B, sorry, Y to the B, yeah. Which, by the way, is square root of R squared times Y to the minus B prime, Y to the B. Yes. This is R times square root of Y to the B minus B prime. If B equals B prime, I know this. I can compute this. And then I say, look, that's it. I just produced an accepting transcript. I'll put these numbers, these three numbers together with B, which is the random coin of the B star, and then declare success. If it doesn't work, meaning if B is different from B prime, then he says, you know what, no problem, let me do it again. Okay? Let me restart the whole process, guess a new B prime, pick a new Z, do it again. Do it and do it and do it until the moment you get an instance where B equals B prime, then you accept and declare success. That's the simulator. The prover doesn't get to do this. The prover gets one shot. Yes. Good. So this is the simulator. I have to show you two things. One, I have to show you that the simulator runs in polynomial time, at least expected polynomial time. Two, I have to show you that whatever the simulator outputs looks exactly like the view instruction. So here I'm actually going to claim perfect indistinguishability. This is precisely exactly the same distribution as the view in that. That's what I'm showing. Okay, so let's show this. All right. how do I show? Well, let's do a hybrid argument. Why not? This is a simple hybrid argument because there's nothing computational, right? Everything looks the same as everything else. Yeah, but you still show. So on the one hand, there is a simulated transcript, which is the output of a probabilistic process. What probabilistic process? This probabilistic process. Right? So that's so this is what, again, pick B prime, I'm just rewriting it. Send something, receive something, send something else. Things don't work, repeat. Yes? Let me look at another probabilistic process, which I'll claim is exactly distributed exactly. What is that probabilistic process? This is where, so the first message here is again r squared y to the minus b prime. Yes? B square root of let me look at the following process. Z is in fact r squared. Yes? The verifier sends whatever b he wants to compute and send. Yeah, it's not necessarily random. Then I compute square root of z. Well, not quite. I toss a coin b prime. Here, not at the beginning. Right. If b prime equals b, then send square root of zy to the b. Else, rewind. Else go back and repeat it. So the only change here, well, two changes. One, the coin b prime was tossed at the end, when the process decided to output something or repeat. Two, the first message was always r squared, just like the real protocol. Yes, I'm getting closer to the real protocol, one step closer. I claim that these two guys are identically distributed. Why is that the case? Well, let's look at the first message. Okay? Let's look at the first message. This is a random square here. As long as y is any square, this guy is a random square. And so is this. So the marginal distribution of the first message, just look at the first message, they look precisely exactly the same. The second message is what? The second message is not under my control. It's something that the verifier computes and sends, so of course they look the same. And the third message is what? I mean, it's a deterministic function of everything that happened before, namely a square root of z times y in this guy to the power b, which is also the same. Yes? Good, except, one second. So the first message is the same, b is the same. And if you look at the first two messages here in this game, yes, what is the information you know about it? Conditioned on the first two messages, what is the distribution of b prime? I claim it is truly random. In other words, if you picked b prime equals 0 versus b prime equals 1, you will see precisely the same distribution of messages. So, I mean, that means I might as well toss my coin here. Yes, I mean, the distribution doesn't change. The ability of the simulator changes. For the simulator to function correctly, this had better be the case. But when I'm analyzing the simulator, I can do all sorts of things. I can toss the coin here, for example. And that would look precisely the same. Now, if you look at this game, what is happening here? I'm running one interaction of the one instance of this protocol, okay? I'm saying, closing my eyes, I'm saying run one instance of the protocol, okay? I flip a coin and I decide to throw it away or keep it with probability half. Okay? And I keep tossing coins. Yeah, I'm not looking at the protocol at all. B prime does not depend on the protocol transfer. So what am I saying? If you have a random variable, okay, yeah, and I do the following process. I say sample from the random variable. With probability half, I keep it. I'm not looking at the sample. Okay? With probability half, I throw it away. Repeat it until you output something. What is the distribution of the object that you output? I claim it is precisely the random variable. If I did look at the transcript and decided to do one thing or the other depending on the transcript, then okay, no good. And that is what happens here, yes. I mean, the transcript, I decide to keep it or throw it away depending on whether B equals something. But what I produce here is indistinguishable from another process where I don't look at the transcript. That's it. Yeah, so that's. Questions? Yes, Andrew.
Is that second one the prover or the simulator?
Here,
Yeah.
this is neither. This is neither, right? This is not the simulator because he doesn't pick the coins here. He's not the prover because the prover never throws anything away.
Because if like b and b prime both equal 1,
Yeah.
and you don't know like square root of y, then you can't really send that over, can you? Or
No, you're right. So you're right. But when I prove that two distributions are indistinguishable, I am not playing the simulator game anymore, right? The simulator has to play this game where he does not know the square root of y.
Mhm.
But the distinguisher is a very, very, very important point. So in this definition, right, the simulator does not know what x is because I have to design one simulator that works for all x. But the distinguisher can actually know what x is. In fact, it can know the square root of x. Yeah. So this is purely a mental experiment. This is the real. This is the simulator. This is what we have to design. Here is the real experiment, the prover. This is something a chimera of.
So the distribution is indistinguishable only when y is a projective residue.
Yes, absolutely. And that's very important, right? So the definition of zero knowledge only gives you guarantees for x in the language. Yes. Why, if you think about it? Because zero knowledge says, I'm going to produce a transcript that looks exactly like the real interaction, yes? In the real interaction, with an honest prover, yes? Of course, yes, we're in a setting where provers. In the real interaction, the honest prover, if he gets a statement not in the language, he would just say, it's not in the language. Yes. That guy is not sound. Claim that this definition does not make any sense for x not in the language. Why is that the case? Because I'm saying that the view here, right? I have to produce something that looks like the view of the real interaction. Okay? What is a real interaction? Where a prover gets a statement that is in the language, right? So an honest prover always gets a statement that is in the language and tries to prove something. For x not in the language, the prover won't even work. The honest prover would not work. So I can only, it only makes sense for yes instances. Clearly, all of what I said, so the indistinguishability of the views only holds true when y is correct. Okay, that's the simulator. Shows zero knowledge. That's it. Now we move on, and we say quadratic reciprocity, very good, right? It turns out that I'd like to show zero knowledge proofs for all NP languages. That includes 3SAT, we-call probability, uncertainty is really every NP language. That's my next goal. Let's see, we can do this part of it today. Please. So what we showed is a very strong type of zero knowledge. It's called perfect zero knowledge. which means that the simulator produces a distribution that is identically distributed to the real. Perfect. It turns out that it's NP-complete languages do not have perfect zero-knowledge protocols. In fact, it's very unlikely that they have perfect zero-knowledge protocols. When I say very unlikely, again, parenthetical remark, how would I put it? If SAT has a perfect zero-knowledge protocol, the theorem of, I believe, ILO has done. Is that what it is? Okay. Some two gentlemen, which I believe are these people, then essentially AM equals AM. Another way to say it is, you should think about it as, roughly speaking, NP equals 1P, which is very unlikely. So it's really extremely unlikely that SAT has a perfect zero-knowledge protocol. So now we have to relax our conditions. We say, you know what, I don't want necessarily the views to be the same. It's enough that they're computationally distinguishable to prolong a time distinguish. Once you make this relaxation, it turns out that all of NP has a zero-knowledge proof, and that's what we'll see. So go right mechanic figures in theorem. Maybe as a computational zero-knowledge proof. Computational refers to the fact that the indistinguishability is it's a computational indistinguishability, assuming that one-way permutations exist. Now, it can also be generalized to one-way functions. But this is something you'll do in the problems. So for now, this is what I'll show. Okay. So to do this, I need to introduce some more machinery, and let me start doing it. This is machinery commitment schemes. Okay, so what is a commitment scheme? It's really, there are two parties again, not a prover and verifier, but rather sender and receiver. The sender has a bit B, and what the sender wants to do is put the bit B inside a locked box and send it to the receiver. Okay, you need two properties. One, when the receiver gets the box, he should know what bit is inside. Yes. Two, later, in a later point of time, the receiver can say, please give me the key. Please open the box. The sender can open the decommit. Please open the box. And no matter what he does, he will not be able to open the box and reveal a different bit from the one he committed. So it's called binding. So I'm bound, once I send the box, I'm bound to the bit. And when I send the box and before I reveal, the receiver has no information about it. That's called hyper. This is what it is. Yeah. So let me define what this is. Alright, so it's a protocol between a sender and receiver. Sender has a bit B, the receiver has nothing. They interact back and forth. And really they interact in two phases. So the first one, I call this the commit phase. And later, there is the reveal phase. Essentially, yeah, we can interact here too, but really I'll talk about sort of one-way interaction. Actually, I'll talk about one-way interaction in both cases. Okay, so this is what it is. And I want two properties. One is hiding. It says that the view of the receiver R, in fact, I want hiding against arbitrary receivers. The receiver may not act honestly in this protocol. So I want for every polynomial time adversarial receiver R star, the view of R star in this interaction, the commit interaction with bit B, with bit 0, is computationally indistinguishable from the view of R star in this interaction. So think about a game where the receiver is arbitrarily malicious. He can do whatever he wants as long as he's polynomial time. The sender has bit 0, they interact, get something. The receiver sees something. The view, which is his random coins together with the messages in the protocol. The other case is when the sender has a bit 1 and they interact. At the end, the receiver cannot tell who he interacted with. Did the sender have a bit 0 or a bit 1? So it's hiding. Let's call this transcript C, the messages, the result of the interaction between S and R is C, the commitment to the bit. And let's call this message D, which is the decommitment, right? So we want, well, even before this, I guess we want correctness. We want correctness. Which says that the receiver R if the sender S is honest, that is, if he acts like what I tell him to do, then the receiver R on input C, the decommitment D, and the bit B accepts. So think about a setting where the sender and the receiver interact, they get a commitment, right, of the message. I'll tell you exactly an instantiation of this protocol, and then maybe it's more concrete and you'll see what is going on. At the end, the sender is committed to a bit B. Okay? And the hiding property says that after the commitment phase, what the receiver sees is indistinguishable between 2 and 0. Correctness says that the sender can reveal some information, a decommitment, some information D, such that the receiver will accept that C is in fact a commitment of B. So this is D is information that convinces the receiver that C is in fact a commitment of B. So that's correctness. And binding says that for every malicious sender, right? So the sender is arbitrarily malicious and it interacts with R, produces a commitment C. So no PPT sender S star can produce C together with D0 and D1 such that the receiver, such that R of C, D0 and 0 equals accept, and R of C, D1, 1 is accept. In other words, the sender is trying to come up with a commitment, and later he can open it to either 0 by giving D0 to the receiver, or open to 1 by giving D1 to the receiver, and he should not be able to do it. And for today, I'm going to say, forget PPT, no sender can do this whatsoever. Let the sender do whatever it wants, it should not be able to do this. Okay, so, is that clear? So how would you design a commitment scheme? So look, I mean, commitment seems so much like encryption, right? To commit to a bit, yeah, the sender encrypts this bit. So of course, you know, That's fine. Under what public key? I mean, it cannot be a public key where the receiver knows the secret key, so he picks a public key secret key. He encrypts the bit under this public key and sends it over to the receiver. Sounds reasonable, yes? Hiding, for sure. And what does he do in the decommitment case? He just reveals the secret key. Yeah? Or he reveals the randomness that he used during the encryption so the receiver can redo the encryption and check that it was not true. Yeah? That sounds good. It's hiding for sure, because it's a good, it's a semantically secure encryption scheme. It's correct for sure, right? I mean, the center can do the right thing, and it's also binding for sure, I guess, right? By the correctness of the encryption scheme, you cannot, I mean, given a ciphertext, it's either a ciphertext of 0 or a ciphertext of 1. Yes? Not really. How many people think, well, I mean, these are all deterministic questions, So this is not such a great strategy, after all. And the issue is that the sender here is a malicious sender. So he can pick public keys and he can encrypt things whichever way he wants. Think about the Goldwasser-Mikhaili encryption scheme. Okay, so what is this? This is the public key is an N and a Y, which is supposedly a quadratic non-residue. Yes, that's the good public key. We know that every encryption is either an encryption of 0 or an encryption of 1. Every number, yeah, is either not an encryption at all, or it's an encryption of 0, or it's an encryption of 1. No number is both an encryption of 0 and an encryption. Yeah, because no number is both a residue and a non-residue. But no number is both a square and a square times y. But that's only true if y is a non-residue. Yes? If y is itself a square, right? So here's the cheating strategy. Right? So the sender picks a public key, which is n and y is a quadratic residue of 1n. And he encrypts to the bit b, which is what? He sends r squared times y to the b. This is the commitment. Later he says, I have to open to b, no problem. I'll reveal r, I'll tell you how I encrypt it. So open to b, I'll tell you r, and you redo the encryption process and you say, well, this square times y to the b equals this, so I'm convinced that this is in fact an encryption. Or I can give you, well, let's say b is actually 0, right? Let's say b is 0. And I'll send you r squared. Open to 0, I just send an r. Open to 1, I send r divided by square root y. Yes. So now if you square this number and multiply by y, which is supposedly how you create an encryption of 1, you will get this number, which will convince you that this is actually an encryption of 1. So this number is both an encryption of 0 and an encryption of 1. And the prover can, he knows the square root of, if you pick the public key together with the square root of y, he can always convince you. So no good. I mean, encryption schemes are not good commitment schemes because a malicious entity can pick the public key. If the public key is picked maliciously, encryption schemes don't give you any guarantees. Certainly don't give you any security guarantees. They don't even give you correctness guarantees. So that's no good as a commitment. So that's the difference between a commitment and an encryption. Yeah? That's why commitments are harder to construct than encryption schemes. They're also easier to construct than public encryption schemes because opening the commitment doesn't have to, I don't have to reveal the secret key. There doesn't have to be a public key secret key. I can reveal the randomness that I used for encryption. Yeah? And so then it doesn't have to be a public key secret key relationship. That's an easier thing to construct. So it's not the same thing. So what we'll show is that if you have one-way permutations, then there are commitment schemes. That's the first step. Okay, so let's very quickly show this. I'll show you the construction. Now the proof, this is something that you should be able to work out yourself. So let's do that. And then we'll move on to actually doing the real work. So how is the commitment? Commitment schemes from one-way permutations. Okay, so let F be a one-way permutation. Here's the commitment scheme. The sender has a bit B, the receiver has nothing. Yes. The sender picks a random R from the domain of the one-way permutation. So let's say it's n bit strings. He sends f of R, the one-way permutation of R, and the hardcore bit of R XOR with the bit B. HCB is the hardcore bit. So if whatever hardcore bit F has, use it. If you don't know anything particular about F, use the Goldberg level. So this is the commitment. So there's no interaction between the sender and the receiver, it's just one shot from the sender to the receiver. So I claim hiding here that given this, the receiver has no cheating strategy at this point. The guy is sitting ducks, okay? So he just sits there, he receives a message. Okay? So no matter what the receiver does, this guy hides B. Why? Because of hardcore bits. Right? What does the decommitment look like? So this is the commitment phase. Decommitment is simply send R. So the receiver says, let me check that this is actually correct. And if it is correct, as an f of this guy is equal to this guy, if it is the case, I am going to compute the hardcore bit of this guy, parity, take the XOR with this guy and get the message. That's it. Okay. Okay, so this is correct, clearly, right? If I commit and then decommit, you will actually accept. Okay. Why is it binding? Right. The claim is really binding. No matter what the sender does, he cannot sort of produce one message and later open it to both a 0 and a 1. Yes?
Because it's a permutation.
It's a permutation. Once he comes up with any number here, there is a unique inverse. It's a permutation. And if there is a unique inverse, the rest of it is a deterministic function of the inverse. Everything is fixed. Yeah? So that's it. So this is a commitment. It's the construction of commitment from one permutation. And you see, if f is indeed not a permutation but rather a one-way function, this would fail. It will still be hiding, still be correct, but it won't be binding. All right, so this is a commitment. Now let's actually show the theorem, the Pro-Technically-Wigderson theorem. In 5 minutes. Not nearly enough. The theorem, but let's sort of start thinking about it. Okay. Good. So, first of all, that theorem is unbelievably broad. Yes. It says for every NP language. It's not saying I'm going to show you a zero-knowledge proof of quadratic reciprocity. It's saying for every NP language, I'm going to construct a zero-knowledge, which is a lot. How would you go about it? Well, you can keep picking NP languages, and for every NP language you construct something, but clearly that's not the way to go. Right? How would you do it? Idea number 0 is this. How would you start showing that theorem? Ideas?
Show for an NP complete.
Show for an NP complete language, yes? So pick an NP complete language, your favorite. Hamiltonicity, very good. 3-sat, very good. 3 coloring, which is what I'll show, very good. It doesn't matter which one I pick. I show a zero-knowledge protocol for the NP complete language. And now, how do I design an NP? How do I design a zero-knowledge protocol for a given language in NP? Use the reduction, use the NP completeness reduction. Namely, take the instance of the language, run the NP completeness reduction, get an instance of 3 coloring, then show protocol. So we know that if the thing that you started with is a yes instance, it's an instance in the language, then this will be a three-colorable graph. And if this is what you got is a three-colorable graph, then the original instance was an instance in the language. So yeah, so this idea 0. Okay, so our favorite NP-complete language, three-colorability, which I'll define in a second. And indeed, you will show a direct zero-knowledge protocol for another NP-complete language, and you have problems. So you can, of course, you can reduce to three coloring, but that's not what I expect. It's uninteresting. Okay, so what is three colorability? It's a language of graphs G. Yes, so graph is three colorable. If you can put a color, you can assign a color to each vertex, rather, you can come up with a mapping from vertices to 0, 1, 2, such that for every edge E, UV, right? Phi of U is different from phi. Yes, you can. That's three colors. Look at every edge. The two vertices are distinct colors. And this is NP-complete. So one of the canonical NP-complete problems. We will design a zero-knowledge protocol for this guy. So that's the baseline. How do you design a zero-knowledge protocol for this guy? Let's get started. You know, those of you who haven't seen, this is too hard. I'm not going to ask this question. So let's get started. And, we'll continue after the spring break, which I assume means that all kinds of states will be erased, but don't party too hard. Or rather, think of zero knowledge when you party. So here's what I'm going to do. Here's the protocol. The prover says, look, you know, both of them know the graph, G, and the prover knows the three coloring, phi. The prover says, let me actually do a random three coloring. I mean, I can renumber the 0, 1, 2 to just permute the colors. No problem, right? This is easy. And the prover says the following, says, let me this is a good graph, yes, I mean. On these nodes, V1, V2, rather, color 1, color 2, color 3, color 4, and color 5. And I want to send this to the verifier, but of course I don't want to send a color to the verifier. It's kind of stupid. Now, zero knowledge is okay. Right? What I'll do is I'll commit to these colors. Yes, so I'm going to just write them this way inside boxes, but that means run a commitment protocol where the message is each of these colors. I just showed a bit commitment, but of course anything is a sequence of bits, so yeah, you can commit to numbers, you know, by writing them as bits. Commit. Okay. So now what is the verifier going to ask? The verifier says, look, I'm going to test you. Okay, this is a challenge. Let me pick a random edge in the graph. E randomly chosen from the set of edges. So E is U comma V, right? So some edge U comma V. And the prover says, let me open the two, the color of U and the color of V. So open, so decommit color of U and color of V. Okay, according to this protocol. And the verifier says, look, let me check that it's a good decommitment, that I actually accept that these two numbers are in fact decommitments of the two boxes, and that color U is distinct from color V. If yes, I say, you know what? Good, I accept. Otherwise, I say reject. That's the protocol. Yes.
How does that guarantee you don't use more than 3 colors?
Good. So one thing I didn't say, okay, in fact, there are three things that the verifier checks. Okay, one, he checks that the commitment is valid. Two, he checks that these colors are actually numbers between 0, 1, or 2, and they're the same. Good, thank you. Great. Yeah. Completeness. Okay, so it's very hard to design a protocol that's not complete. So it's I'll leave it to you to verify. Soundness, because if the graph is not three colorable, then the prover can cheat in one of two ways. One, what you said, I can put I can four color the graph. Okay, or I can put the same color on some edge. That's the only way. I mean, given that the commitment is perfectly binding, the first message uniquely commits the prover to colors here. So the only possibility is that these colors are either invalid, is a 3 instead of 0, 1, 2, or two colors are the same. In either case, the verifier will catch this. So if you pick a random edge, right? What is the probability that I land on one of these sort of bad vertices? Right? It's at least 1 over e. If two colors are the same, that's what the prover did, I'll catch it with 1 over e probability. If one of the vertices is bad, I'll catch it with 1 over v probability. But of course, that's hopefully at least 1 over e. So the probability that a malicious prover can make the verifier accept is at most the probability for every graph not three colorable. The probability that the verifier outputs v outputs 1 on interaction with any p star is at most 1 minus 1 over e. Right? So it'll reject with probability at least 1 over it. It'll accept with probability at most this number, which is less than 1. Okay, that's really what I mean. Now, if I don't want 1 minus 1 over e, repeat it many times. Repeat it how? Run it again the next time, run it again the next time. Keep going. You run it for e times k times, right? And the soundness. Repeat e times k times. The soundness is at most 1 minus 1 over e to the power e times k, which is at most e to the minus k. And that, On the other hand, completeness is completeness 1, right? So every time the prover will manage to convince the verifier if the graph is three colorable. That's the protocol. Zero knowledge, that's for next class. Close to spring. Okay. All right, have fun.
You did the repetition with a new coloring.
Say again.
You did that repetition with a new coloring.
Excellent. When I say repeat, I mean repeat the whole thing, which means pick a new permutation of the colors. Right. So the first thing is permute the colors. Right. Those are the C1 up to C5, and then commit. The next time you repeat, randomly, don't use the same colors. You'll be in trouble if you. You can see why you will be in trouble with zero knowledge, right? Because the verifier is going to ask to open all possible edges eventually, and then you're dead. So you have to, absolutely. Very good. Okay. So next class.